Hey everyone, and welcome. So today we're going to tackle a huge idea in calculus, something that on the surface feels super simple, but underneath, well, it's got some real mathematical muscle. We're talking about continuity, and we're going to break down what it really means for a function to be continuous.
So let me ask you a simple question. Could you draw this graph without lifting your pencil off the paper? You see, at its core, that's what continuity is all about. It's that gut feeling you get when you can trace a curve and there are no breaks, no gaps, no weird jumps. But you know, a gut feeling isn't going to cut it in a math class. So today, we're going to take that simple idea and forge it into a rock-solid mathematical definition. All right, so here's the game plan. We're going to start with that simple pencil test. From there, we'll build up the 3 official rules of continuity. Then we'll check out all the different ways a function can break, what mathematicians call discontinuities. After that, we'll see why this all matters, the real power behind it. And we'll wrap up with a really powerful guarantee that continuity gives us. Sound good? Let's dive in.
All right, first stop on our journey, the pencil test. This is our starting point. It's all about moving from a simple gut feeling to a real mathematical idea.
So, here it is, the basic idea. A function is continuous if you can just trace its graph without picking up your pencil. Simple, right? No gaps, no holes, no weird jumps. And look, this is a fantastic way to think about it, to build your intuition. But here's the catch. Lifting the pencil isn't exactly a term you'll find in a math proof. We need something more concrete, more rigorous. So, how do we build that formal definition? Well, we're going to do something kind of clever. Instead of looking at perfect graphs, we're going to become detectives and investigate broken graphs. We'll figure out exactly why they fail the pencil test, and each clue, each failure, is going to give us one of our rules. Okay, Exhibit A. Take a look at this graph. See how the curve is coming along nicely from the left and coming along nicely from the right? It looks like they're about to meet up at this point we'll call A. But then, poof, there's a hole. Right at A, the function just doesn't exist. You'd literally have to lift your pencil to hop over that gap. And that's our first problem. The function isn't even defined there. And that leads us straight to our very first rule. It's the most basic check of them all. For a function to be continuous at some point A, the function has to exist at A. In other words, f of A has to be a real number. Simple as that, no holes. Okay, but what about this case? Look, at point A, the function is defined. We've got that solid dot right there. So rule number 1 is satisfied. But come on, you'd still have to lift your pencil, right? The whole thing is clearly broken. The problem here is that the graph is heading to one place from the left, but it's coming from a totally different place on the right. It's a sudden jump. So this uncovers our second big rule. It's not enough for the point to just be there. The function has to be approaching the same spot from both sides. This is where the whole idea of a limit comes in. For the limit, as x approaches A to exist, the left-hand limit and the right-hand limit have to agree. If they're heading to different places, like in that last graph, the limit doesn't exist, and boom, the function is discontinuous. All right, time for the final piece of the puzzle. Check this out. Let's run through our checklist. Rule number 1, does f of A exist? Yep, it's that little dot floating up there. Rule number 2, does the limit exist? Well, yeah, the curve is heading towards the exact same spot from the left and the right, so both rules are met. But the graph is still broken. You'd have to draw the curve, then lift your pencil to go put that one dot in a totally different spot. The point exists, the limit exists, but they just don't match up. And that, my friends, gives us our third and final rule. This is the one that ties it all together. The spot the function is approaching, that's the limit, has to be the exact same spot as the function's actual value. The limit has to equal the function value. You can't just have a point existing somewhere else. The point has to be exactly where it's supposed to be, filling the hole perfectly. And there you have it. That's the official 3-part definition of continuity. By looking at all the ways a graph could be broken, we've built a foolproof test. First, the point has to exist. Second, the limit has to exist. And third, the limit has to equal the point. All 3 have to be true. If even one of those fails, you've got a discontinuity. Okay, so now that we know the rules, let's talk about the rule breakers. We're going to look at the different kinds of breaks a function can have. Mathematicians actually have names for these things, so we can be really specific about what kind of problem we're looking at. First up, we have what I like to call the friendliest type of break, a removable discontinuity.
Think of this as a super easy fix. It's basically just a single hole in an otherwise perfect graph. The limit exists, everything is heading to the right place. It's just that one little point is either missing or in the wrong spot. You could literally remove the problem by plugging that one hole. Yeah, this visual shows it perfectly. It's like a missing pixel in a digital image. The rest of the picture is fine, there's just one tiny spot missing. All you'd have to do is fill in that one dot right where the limit says it should be, and the whole thing would be continuous. A tiny, repairable glitch.
Next up is the jump discontinuity. We've actually already seen one of these. This is where the function is cruising along and then, bam, it suddenly jumps to a completely different level. It's not flying off to infinity or anything crazy. It's just that the value from the left side and the value from the right side are two different finite numbers. It's like the graph teleports. And this picture really nails it. It's like a staircase where a step is just gone. You're walking on one level, and to get to the next part of the path, you have to take a big, sudden leap. There's a clear, measurable gap there that you just can't draw without lifting your pencil. And finally, we have the most dramatic break of all, the infinite discontinuity. This is where things get wild. As the function gets closer to a certain x value, the y value just explodes. It shoots straight up to positive infinity or plummets down to negative infinity. There's no containing it.
You've probably seen these before and called them vertical asymptotes, and that's exactly what they are. This isn't a simple hole or a jump, it's a fundamental chasm in the graph. There is absolutely no way to bridge this kind of gap. The function's value is just off the charts.
Okay, so we've got rules, we've got names for the different kinds of breaks, but you might be asking, so what? Why do we care so much about being this precise? Well, the answer is that having this rock-solid definition of continuity unlocks some of the most powerful tools in all of calculus. It's a real game changer. For example, take a look at this. It's called the composite function theorem, and it's a super useful trick. Basically, it says that if you're taking the limit of a function that's inside another continuous function, you can do something that feels a little bit like cheating. You can actually pass the limit through the outer function and apply it directly to the inside one. Now, that might sound a little abstract, but trust me, when you're dealing with really messy limits, this is an absolute lifesaver. All right, this brings us to our grand finale. We're going to look at one of the most famous and honestly beautiful results that comes directly from this idea of continuity. It's called the intermediate value theorem, or as we like to call it, the IVT. And when you see it on a graph, the IVT is so intuitive it almost feels obvious. Here's what it says. If you have a continuous function, no breaks, remember, between 2 points, say point A and point B, then that function must hit every single height, every single y value in between. It's like this. If you drive your car from sea level up to an altitude of 1,000 feet, you can't just magically skip being at 500 feet. At some point, you had to pass through every single altitude in between. Continuity guarantees it. Now, one of the coolest things you can do with the IVT is prove that solutions to equations exist, even if you can't find them. Take a look at this table. We have this function, f of x equals x minus cosine of x. At x equals 0, the function's value is -1. It's negative. A little later, at x equals pi over 2, its value is positive. Now, think about it. If the function is continuous, how can it get from a negative number to a positive number? It has to cross 0 somewhere in between, right? And just like that, without doing any algebra, we have just proven with 100% certainty that this equation has a solution. That's pretty powerful. But here's a crucial catch. The intermediate value theorem is what we call an existence theorem. It's a guarantee that there's a solution somewhere in that interval. But notice, it only guarantees there's at least one solution. What if the graph wiggles up and down? It could cross 0, 3, or 5, or 100 times. Which leaves us with a great final question to chew on. The IVT tells us there's at least one solution, but how could we know if there's exactly one? Well, that, my friends, is a question that leads us even deeper into the world of calculus. Thanks for joining me.